thank you for all friends attending to my presentation. And if I speak in English not very well, you can ask me a question and I can answer you in another languages. My topic is the dynamic Shapley value in the game with spanning tree, because I'm interested in the field of dynamic game and the minimum cost spanning tree game. This is the outline of the report, and at first I'd like to ask 3 questions answered my model. What is this model and what happened to the model during the game process, and how to modify solution of this game model in order to get a result we want. In order to answer first question, it is n players and a 2-stage game, and in each stage, a minimum cost spanning tree game is played, and after first stage, assume a particular player M may leave the game with a probability. This probability is depends on player M's position in first stage. So how happened the model during the game process? After first stage, player M may be stay in the game, maybe leave the game, and how to modify the solution of this game. At first, the solution based on the concept from my supervisor, Peter Xiang, in 2006, about the time consistent of corporate solution concept. And second, I used the previous result from my paper using the imputation distribution procedure to construct a dynamic Shapley value. And it is important if we strictly use dynamic Shapley value in these dynamic games may be time inconsistent. Here are several important definitions. We assume in the game there are n players, and the set 0 is denoted is the source denoted by set 0, and the definition of graph, the set of edges, and the concept about connected graph is divided as below. And it's important for us to consider how players construct a minimum cost spanning tree in dynamic situations. At first, the graph with the spanning tree consists of 2 important parts. First is a graph. Second is a cost of matrix. The cost of connections is represented by a cost matrix, like a formula, like first formula. Each of the element of cost matrix is decided by only 2 players. These 2 players, it means the cost of between them only decided by themselves. And in these 2-stage games, at each stage, arbitrary player may choose a vector. This vector, each of the element of the vector is player I against player G. And and each stage, according to the definition of strategy of player, we can define the cost of edge is divided as follow. So for arbitrary edge between player I and G, the cost of edge CIG is equal to CGI. is divided by a mapping from strategy of players IG to the set of all possible cost of edges. It's a real number. For example, let's look at this figure. For example, this is a 5-person game, and in the center, it is the source 0 for arbitrary edge. C 4 3 4 and the cost 4 3. The edge of cost 3 4 is equal to the cost of edge 4 3 is equal to cost function FC. FC is decided by x3 and x4. x3 it is player x3 4. It is the strategy of player 3 against player 4, and x4 3. It is a strategy of player 3 against x4 3. It is a strategy of player 4 against player 3. Each element, each strategy is from the set of strategy of players. So when all players simultaneously define the strategy profiles x1, 2, 3, 4, 5, at the same time, the graph will be divided. In this research, we assume that the game based on full graph. So this full graph with restricted cost matrix, we can get a graph, and in the graph we use our algorithm to calculate the minimum cost spending tree. The definition of minimum cost spending tree like this. It is a minimum cost of edges when this spending tree minimum cost spending tree, it is minimum cost spending tree. It is a connected graph with no circle, and the minimum cost is minimum between of them. This is the definition of minimum cost spending tree and his total cost. So like a previous example, we define a graph with cost matrix, and we can find a minimum cost spending tree from it. The algorithm of minimum cost spending tree is from series graph. So let's describe the game. As I said, it is a two-stage game. At first stage, all players simultaneously choose their behaviors, and after first stage, if player M stay in the game played repeatedly, and all players select strategy profiles as same. But if M leaves the game, the graph is changed because the set of players is changed. Now is N minus M. So how to define the probability that player M leaves the game or not leave? We introduce a definition concept about P divided like a formula same of formula 7. In the formula, BM denoted the set of all edges of the subtree with root M in the minimum cost spending tree. It is the Unicode subtree in the minimum cost spending tree. For example, like this picture, in this finger, all verticals in yellow are verticals in BM. It means in reality, it means if M wanted to connect to the source 0, he has a unique path from M to 0. But another verticals, if they want to connect to 0, the source 0, they have to through M. So all verticals like this would be BM, and they will give M more pressures. And if the pressures bigger, the probability of M leave the game is larger. So as I described about this process of the game, we can define the characteristic function. The characteristic function, the method of characteristic function is from works Parina several years ago, and in two-stage games, are shown that the total cost of the players is the sum of cost of players on both sides, on both stages. And we use Bellman equations. We can get we can use this formula, and the P divided by formula same, and if we can find the strategy X bar, then this X bar is called a cooperative strategy, and the strategy profile is called cooperative strategy profile. So let's consider the characteristic function for correlation S. In minimum cost spanning tree, as various researchers by other scientists, characteristic function for correlation S. We in this research we have shown that only collections players in collection S wanted to connect to the source, but the correlation N without S, they don't want to connect to the source. And they don't want to end any help to correlation S. So in a similar way, given subset S, and we use the result from BERT define the worth of correlation S. VS as the minimal cost spending connecting all players to the source. In this situation, I show that N without S are disconnected, and they will not end any help to correlation S. This is the definition of characteristic function for correlation S. When M in the correlation has when M in the correlation, the characteristic function for correlation S defined as is similar to grand correlation. But if M in the correlation S, okay, I make a small mistakes. In this slide, the formula is M in correlation S. So the formula of characteristic function for correlation S is similar to the characteristic function for grad correlations. But if M not in S, it's just two the characteristic function for correlation S is just summarized by first and second stage. Of course, if correlation S is non-empty, then the value of characteristic function for correlation S is equal to 0. So this is the diagram of the game. For example, at the first stage, the minimum cost mean tree like this, and if M stay in the game, maybe they could find another minimum cost mean tree, and the total cost is minimal between in dynamic games. Or player M leaves the game, they have only the game only has n-1 players, and they play the game like a first stage. So we can define the characteristic function of sum game. Because it is a two-stage game, the sum game is only one stage game at second stage. If M stay in the sum game, the grad correlation has n players, and if M not in the subgames, the grad correlation only has n-1 players. And according to definitions of all above, we can define the Shapley value in two-stage minimum cost mean-tree game. In second stage, if M is not in subgame, the Shapley value is defined like this, and M stay in the game is defined like this. If M not in the subgame, we know that the grad correlation has only n-1 players, so the Shapley value is equal to like this. Is different before. The formula is different from before. Time consistent of complete solution concept was introduced by Petrosian in 2006, and we use imputation distribution procedure can construct a dynamic Shapley value. The beta, it is a scheme for two-stage minimum cost magnitude game, and we can calculate beta. If beta, if in the game with spanning tree, if there is exist a non-negative IDP, satisfies following, then this dynamic Shapley value is called time consistent. But unfortunately, the dynamic Shapley value with IDP defined by before always time inconsistent. So in my research, I planned I introduced two theorems in order to modify the Shapley value, modify dynamic Shapley value, and make it time consistent. In first theorem, if in the game, if player M maybe leaves the game, and the game satisfies several solutions, then the dynamic Shapley value constructed according to before is time consistent. Similarly, in second stage, it is a more more 这个单词怎么说？In second theory, we have another conditions to modify the dynamic Shapley value and make it time consistent. Here are several important publications. Thank you.
Thank you very much. Anyone has any questions? Um, uh, if not, maybe could you please introduce in a few words the main idea of cost-spanning tree game? Only the main idea. Maybe not all of the participants know this, so maybe it's important.
Okay.
Maybe not.
Okay. At the beginning of my research, I'm interested in dynamic games with complete information. But if I read some papers about the minimum cost benefit game, I knew that in coalition games, it is an interesting game because it has a, cooperative game. It has a it is a cooperative game. It also a network game. Uh, but I read many papers and I knew that there are less researchers studied minimum cost spending tree game in dynamic situations. So I started research it, and in this report, I use a model from Setgolf Petrosyan in 2015. The model about two end-stage game with shock. So I'm interested in minimum cost military game where players are changed. If in minimum cost military game, a player the structure of graph is changing. Of course, the minimum cost military is changed as well. So I'd like to consider about how to modify a time consistent solution for these special situations. Of course, my model is simple, but I have published several different fields about spanning tree with dynamic situations. For example, minimum cost forest game in dynamic situation, and minimum cost spanning tree with perishable products. Uh, so the main point of this report is modify a time consistent solution for minimum cost management in dynamic situations. Yes.
Um, maybe I have a simple conceptual question,
Okay.
but anyway, I'm very interested to ask. So, um, for example, we take a real life example of one build, one road, right?
Yes.
And in one build, one road, there are several participants. And for example, a road network or railway network
Yes.
between participants, such as China, Russia, Kazakhstan, Mongolia, other countries, yes, related to or that are located nearby the one build, one road. Maybe some European countries. And well, maybe the idea of the minimum cost spanning tree is to build the connection or to build a communication channel or railroad channel fast enough and with a minimum cost, so that um, um, to connect all these countries that are connected to one build, one road, right? And um, uh, when you study the time consistent solution of the cooperative on cost spanning tree, uh, does it reflect the time consistency of the minimum cost spanning tree in this model? For example, if some profits of some players changes in time, whether this time consistency cooperative solution supports that the cost spanning tree will hold, will always optimal for all of the participants to have this kind of communication or railroad or road structure, so that nothing will change, and in what we invest, how we build the road, how we build communication between countries or companies in this will not change. I don't know. Maybe my question is strange, but anyway, I'm very interested.
Yes, it's a good question because in reality, now we have in China we have a police. We have state police one road one build. Exactly, we have planned to construct transportation networks between Russia, Kazakhstan, China, Mongolia. If we can we can use a mathematical model to consider the transportation network, and we can use if we can construct a optimal principle to ensure that the cooperation in the future is always time consistent. It is a wonderful idea. But it's much more complexity from this report. Yes.
I know, but the question is not the cooperative solution will be time consistent, but also the minimum cost spanning tree that we have built will be time consistent, because minimum cost spanning tree reflects the can reflect the road. Yes, maybe some of the participant will not participate in the cooperation in future. He will not be interested, or maybe later the new roads will be open. So the road that we have built using the minimum cost spanning tree approach or communication that we will build will not be interesting in future. So how to ensure that the minimum cost spanning tree will not change in time? Time consistency of minimum cost spanning tree. Maybe my question is strange, I don't know, but anyway.
I don't know your English. В смысле?
Ну, может быть, времени мало. Вот,
Окей, ну сразу и отвечу.
да, ты исследуешь динамическую устойчивость
Да,
минимум кооперативного решения, правильно?
да, правильно.
Но минимум cost spanning tree тоже основное дерево может меняться во времени, правильно?
Да, конечно.
Но может быть, когда минимум cost spanning tree это дороги, это очень дорого.
Да, конечно.
Мы не хотим, чтобы дороги, оптимальные дороги между странами менялись. Зачем? Мы хотим, чтобы то, что мы построили, всегда
Да,
было
да,
оптимально.
да,
Можно ли
я
исследовать
понимаю.
динамическую устойчивость самого минимум cost spanning tree? И как это связано с кооперативным решением? Это должно быть связано
Да,
обязательно.
я понимаю. В принципе, в классической ситуации люди занимаются минимум cost management, потому что они хотят разделить расходы, когда они строят вместе дорогу. На самом деле,
Можно
мой
по-китайски
мотив...
лучше. Лучше по-китайски, тогда все
Окей, окей.
поймут.
In my model, if not only consider how to construct roads between several cities, also can consider about how to divide it, cost between players. So in your question, you ask about road is very expensive. So in the future, if exchanged, what happened? But not only roads, because in each year, the transportation network has many cost, not only in construction, but also transportation fee and for example, in another research, perishable products. Perishable products, it means product like fish. We use the transportation network. If the transportation network has a different distance, the loss of perishable product is different. So maybe for state game, for state game, one state game, not dynamic game. your question is important. How to divide cost between cities because they want to construct a road connect each other. But in dynamic situations has another question. So your question is not in my model, but it is important in reality. Yes.